Before this study was conducted, the fire service had a lot of practical knowledge about ventilation, but the science was lacking. The previous research fell short of creating experiments that would give the fire service the necessary details to ventilate intelligently. In this module, we will provide an overview of the experiments conducted as part of this study that led to the tactical considerations presented later in the course. At the time of this study, residential window failure data was lacking. Several fire performance experiments were conducted in the laboratory at Underwriters Laboratories in Northbrook, Illinois, to address this knowledge gap and guide ventilation parameters for the full-scale fire tests. These experiments were designed to identify and quantify the self-ventilation performance of modern and legacy windows in a fire event before fire service arrival. An additional experiment was conducted to examine interior door performance. Click the icon to learn more about the experimental samples, methodology, and specific test results, or click Next to skip to a summary of the findings. The fire performance tests utilized Underwriters Laboratories' full-scale vertical fire furnace. This panel furnace is one of 3 major furnaces at UL used to evaluate the fire endurance characteristics of representative building sections. Click each tab to learn more about the experimental methodology. The first 3 experiments were conducted with samples A, B, and C. After each experiment, the windows were rotated to the next slot in the frame until every window was tested in each location. Experiments 4 through 6 were conducted with samples D, E, and F, and were rotated just as the first 3 were. Throughout the test, observations were made to note the character of the fire and its control, the condition of the exposed and unexposed surfaces, and all developments pertaining to the fire performance of the assembly, with particular reference to stability, heat transmission, the passage of flame, and generation of smoke. It is beyond the scope of this online training course to present all of the experimental results. You may download a copy of the technical report from the resources section for that level of detail. Click each box to view a summary of the window and door experiment results. To get a fair performance comparison between the windows, it is essential to ensure each window's exposure is comparable. It was impossible to perform a large number of experiments, so 3 windows were tested at once to maximize resources. To improve repeatability, the windows were rotated between bays in the frame so that each window was in each location once. Pillars were built into the furnace between windows to decrease the impact of one window failing on the other window's exposure. This chart shows the furnace temperature for each window experiment versus time. The average furnace temperatures were within 20% for the first 3 minutes, 10% from minute 3 to 5, and 6% for the remainder. Another measure of repeatability used was the heat flux to the window assemblies. Heat fluxes for all the gauges for every experiment are within 20%. These experiments demonstrate a significant difference in legacy and modern windows and doors exposed to fire conditions. In this limited series of experiments, the legacy single-glaze windows outperformed the modern double-glaze windows in terms of longer failure times. The 4 modern windows' average failure time was 4 minutes and 34 seconds, while the average failure time for the 2 legacy windows was 11 minutes and 52 seconds. It is proposed that this occurred for two reasons. First, the legacy windows had thicker glazing than the modern windows. Second, the way the glass was fixed into the frame differed significantly between the two eras. The legacy window glass was held in place with a putty-like substance, so there was room in the frame for expansion of the glass. The modern glass was fixed very tightly into the frame with an airtight gasket and metal band. This configuration did not allow for much expansion and therefore stressed the glass as it heated and expanded. The average door failure time was 5 minutes and 10 seconds. The hollow core doors and the solid door with the panels failed at approximately the same time because the panels were cut into the solid door, making them as thin as the hollow core wood components. While the primary purpose of these experiments was to establish some baseline data on window failure to guide the ventilation parameters for the full-scale experiments, the findings can help us better interpret thermal imaging data observed during the size-up of a residential structure fire. During window experiments 1 through 3, we noticed in the thermal imaging camera view that the modern window hid the fact that there was a fire behind it for a significant time compared to the legacy windows. This is likely due to the energy-efficient design of the modern window. Here we see the thermal imaging view of the 3 windows 7 seconds after ignition. The heat from the furnace is immediately conducted to the exterior of the legacy windows, but it is not visible in the modern window. The image at 1 minute and 30 seconds shows that the modern window allows as much heat through as the gypsum board on the inside of the assembly, while temperatures above 150 C or 300 F are detected on the legacy windows. Here we see that heat is now visible through the window, and the first crack is developed through the outer upper pane. At 4 minutes and 27 seconds, the modern window upper pane has failed, and the temperature registers the same as that of the still intact legacy windows. The temperature inside the modern window at 1 minute and 30 seconds is over 315 degrees C or 600 degrees Fahrenheit, but is not detectable outside with the thermal imaging camera. This is important when thermal imaging cameras are being used for the size-up of structure fires. The first elevated temperature, or the red in the images, detected by the thermal imaging camera came after a window failure. Even slight temperature differentials noticed with the camera when looking at modern windows may indicate elevated temperatures in the structure. To examine ventilation practices and the impact of the modern fire environment on fire behavior, 2 test structures were constructed in the large fire laboratory at Underwriters Laboratories in Northbrook, Illinois. 15 experiments were conducted to examine a variety of ventilation scenarios. Click the icon to learn more about the test structures, instrumentation, fuel load, and specific test results, or click Next to skip to a summary of the findings. 7 of the experiments took place in the one-story ranch-style structure shown here. A residential architectural company designed the house to be representative of a home constructed in the mid-20th century. The 1,200 square foot house had 3 bedrooms and 1 bathroom. Walls and doorways separated all of the rooms, and the ceiling height was 8 feet. The remaining 8 experiments were conducted in the 2-story colonial-style structure shown here. The 3,200 square foot house had 4 bedrooms and 2.5 baths. The home featured an open floor plan typical of modern construction. During the experiments, gas temperature, velocity, and concentration were measured, and video footage was captured. Click the tabs to see more information. The gas temperature was measured with bare bead Type K thermocouples. Thermocouple arrays were located in every room. The gas velocity was measured utilizing differential pressure transducers connected to bidirectional velocity probes. These probes were located in the front doorway and the window used for ventilation. Thermocouples were co-located with the bidirectional probes to complete the gas velocity measurement. The concentration of oxygen, carbon monoxide, and carbon dioxide was measured in 4 locations within the test structure. Video cameras were placed inside and outside the building to monitor both smoke and fire conditions throughout each experiment. 8 video camera views were recorded during each test. The fuel load was standardized to ensure consistency from one experiment to the next. Click the buttons to view more details. The living room in the 1-story house, as well as the family room and the living room in the 2-story house, was furnished with 2 sofas, an armoire, an end table, a coffee table, 1 chair, a television, a lamp with a shade, 2 framed pictures, and 2 curtains. The floor was covered with polyurethane foam padding and polyester carpet. The 2-story house also had a den on the first floor, furnished with a stuffed chair. The master bedroom in both structures was furnished with a queen-size bed, dresser, armoire, and television. The wood frame bed consisted of a mattress and box spring covered with a comforter and topped with 2 pillows. The floor was covered with polyurethane foam padding and polyester carpet. The additional bedrooms were furnished with the same bed, featuring a wooden headboard, a dresser, armoire, television, and framed mirror. The floor was covered with polyurethane foam padding and polyester carpet. The dining room was furnished with a solid wood table and 4 upholstered chairs. The kitchen was furnished with the same table and chairs as the dining room, a dishwasher, stove, and refrigerator. The simulated OSB base cabinets were topped with cement board counters, and the floors were covered with cement board to simulate tile flooring. The experiments began with the exterior doors and windows closed and the interior doors consistently open or closed as designated. The fire was remotely ignited in the living room sofa of the 1-story house or the family room sofa of the 2-story house. The fire was allowed to grow until ventilation operations were simulated. Ventilation time was determined based on 3 factors: time to achieve ventilation-limited conditions in the house, potential response and intervention times of the fire service, and window failure times obtained from the furnace experiments. The 1-story house was ventilated at 8 minutes, and the 2-story house was ventilated at 10 minutes. Ventilation scenarios included ventilating the front door only, opening the front door and a window near and remote from the seat of the fire, opening a window only, and ventilating a higher opening in the 2-story house. When more than one ventilation opening was created, the subsequent openings were made at 15-second intervals. After ventilation, the fire was allowed to grow until flashover or perceived maximum burning rate based on the temperatures, observation of exterior conditions, and monitoring of the internal video. Once the fire maintained a peak for some time, with respect given to wall lining integrity, a hose stream was introduced through an external opening. At the conclusion of every experiment, a stream of water was directed into a ventilation opening for 10 seconds. The purpose of this flow was not to extinguish the fire, but to suppress the burning gases and see if there was an impact on the surrounding rooms as it pertains to pushing fire. The experiment was terminated approximately 1 minute after the hose stream, and suppression was completed by a deluge sprinkler system and the firefighting crew. This table describes all of the experiments. Click the numbers to view a 3-dimensional picture of the house with the ventilation openings highlighted and a timeline of experimental events. It is beyond the scope of this online training course to present all of the experimental results. You may download a copy of the technical report from the resources section for that level of detail. Click for a summary of the key factors evaluated, which drove the tactical considerations presented later in this course. The fire service's core mission is life safety, both their own and that of occupants. These experiments allowed for the assessment of tenability before fire department intervention and after fire department intervention. 2 measures of tenability were used: temperature and gas concentration. While most of the houses were untenable, there were locations in which occupants could need to be rescued. Several variables beyond the 2 measurements described above could lead to the incapacitation or death in a fire scenario. Some of them are the exposure time, the rate of change of the exposure, the susceptibility of a particular individual, or any pre-existing antagonistic conditions. It has also been well studied that these measures have additive effects. For example, an oxygen-deficient environment could cause an individual to breathe faster, increasing the intake of CO and hot gases. An important factor when analyzing ventilation is how long it takes for the fire to respond to the air provided by the ventilation event and when the environment becomes untenable for firefighters operating in the structure. To examine this, the time of ventilation was subtracted from the time of untenability. Looking closer at this time window, you can see when the temperature begins to rise and at what rate. This could be the time firefighters notice there is a problem and how long they have to evacuate. The repeatability of these experiments was examined by comparing the first 8 minutes of the one-story experiments and the first 10 minutes of the two-story experiments. Additionally, 2 scenarios were run in triplicate for each structure to compare the entire experimental series repeatability. As a whole, this set of experiments showed good repeatability. These experiments provided significant insight into the impact of the modern fire environment and ventilation practices on fire behavior. The results have been translated into tactical considerations for the fire service presented in the next module. The 3 key findings that drove the tactical considerations are summarized here. The amount of air and the location that the air is supplied to a ventilation-limited fire changes how much energy a fire generates and how fast it generates it. The amount of air and the location that the air is supplied. The main guidance firefighters are given in their basic ventilation training is to ventilate as close to the seat of the fire as possible. This is meant to localize the growth of the fire to the area of origin. Ventilating remote from the seat of the fire creates the potential to spread the fire to uninvolved parts of the house by creating a flow path and source of oxygen from the uninvolved area. When determining how to ventilate a room most effectively, it would be intuitive to ventilate near the top of the room since that is where the hot gases from a fire develop a layer. One must also consider how the cool air enters the room as the hot gases are leaving the room. If the available fuel needs the cool air entering the room, then the room will transition to flashover, and the burning will take place at the ventilation locations, leaving the room fully involved in flames.